Continuing on project number 2 discussion, after your raster plots, the next thing I've asked you to make for both neurons are peri-event time histograms or peri-stimulus time histograms. These are basically histograms of times at which neurons fire. So here are some examples. So let's say this is an onset of an event or a stimulus presentation. You see the raster plots showing one of the neurons really fired this much time after that stimulus onset. This is a nice way to basically convert this two-dimensional plot into a one-dimensional plot. It allows you to quantify it and do maybe more, analysis on it and so forth. Okay, the idea is that you have small bins. You're basically counting the number of spikes that are in that bin. You're obviously normalizing by the number of trials, because the more trials you have, the more spikes that are likely to be in your bin. It's especially important for project number 2 because if you look at it, the number of trials per direction are not the same. Okay, and basically, for instance, a bin here would have a higher value, as you can see. Okay, and then compared to that, this neuron really didn't fire all that much in response to the stimulus compared to this one. This also allows us to, again, compare maybe different neurons, or maybe this was the same neuron, but this was a different stimuli, and so on and so forth. Okay, so going back to the project description, I once again have a hint on how you might do this. Okay, here PSTH is not a function. Okay, this is a variable that I created. This is a variable that you're going to have to initialize to 0 because we're going to keep adding things to it. Okay, so his C is a function, and it allows you to, for instance, those spike times that you computed per trial, per your direction, it will basically bin it with respect to some edges that you define, and I've defined those edges for you. I want you to bin them in basically minus 20 milliseconds. So if you use this already, his C will give you what you're looking for. Okay, there was a here I basically have made PSTH a column vector. Now his C sometimes returns column vectors, sometimes it returns row vectors. So I had made a discussion point in e-learning about this, and let me pull that here. Okay. Okay, so for instance, PSTH is zeros, length, edges, peri, and there's going to be, 8 directions of them. Okay, if you set your spike times vector to be a row vector, which that is what I did, then the following works. So you type his C, spike times, edges, peri, and you ask it to return 2. And then if you transpose that, this works. If you have your spike times to be a column vector, then this one works. So the 1 or 2 inside force it to return a row vector or column vector. If not declared at random times, it returns column vectors. Other times it returns row vectors. I don't know why it has done it that way. Again, just you set it up and try these different combinations. Again, looking at your raster plots, you should be able to visually see whether your stimulus time histogram makes sense or not. Obviously, if you see a lot of spiking, they should add up to a big one. If there isn't much, it should be a small blip. Okay, and I have asked you to once again plot these peri-stimulus time histograms in this format. So put the proper histogram in its proper direction. By the way, this figure 3 and these figure 2 do not correspond to the neurons that I gave you. This was another neuron, and it was a definitely untuned neuron. Okay, so your neurons are a bit more tuned. But even looking at this, you can see this neuron did fire a little bit before time 0 and really didn't have much afterwards. So for instance, this peri-event time histogram makes sense because it's almost flat afterwards. And this one ended up firing a bit towards the end, and you can see that's basically reflected in here. Okay, so again, comparing this with the peri-event time histograms or peri-stimulus time histograms you should be able to figure out whether you did it right or wrong. Okay, and finally, the last thing I've asked you to do is to plot a tuning curve for these. Okay, and you should be able to do so by just adding all of these up. Okay, because I've asked you to do it after time 0 to time 1. All right, so if you have this PSTH value, you just need to find the last half of it and add them up. And going back to the class notes, this is what a tuning curve, for instance, looks like. In your case, in this case of this project, the directions will be 0, 45, 90, and so on, all the way to 315 degrees. So just plot these dots and combine them together. That will be your tuning curve. If you do download and read Georgopoulos' work, he tried to fit them into Gaussian curves. That's not required. For instance, I think that's what they did also. They fit it into a Gaussian curve. That is not required, but if you do that, that's fine. You'll get extra credit for it, maybe, if you do it right. It's not too hard to do in MATLAB, but again, it's not mandatory given that you guys have to do raster plots and peri-event time histograms. I didn't want you to also deal with Gaussian fitting of the tuning curves. Okay, I will upload these 2 videos. And then I will hold office hours as usual. And as always, you can send me questions through email.